So let's see this problem. Now in this problem we have to do the acceleration analysis, wherein this mechanism is given. We have drawn the given mechanism, configuration of the given mechanism in the scale of 1:2, where the crank length OA is given as 4 centimeter. The connecting rods AB and AC, they are equal. That length is given, and the omega of crank, that is angular velocity of the crank, is given to us, which is in the configuration diagram it is shown as clockwise, and the magnitude is 60 radians per second. So if we see this configuration, this is a double slider mechanism. So single crank is driving two sliders, and the angle of the crank with the vertical or the horizontal, this is given as 45 degrees. So in this configuration, this angle is 45 degrees. Now the line of stroke of the slider B and slider D, they are perpendicular to each other, or the line of actions or line of the strokes of these two sliders is 90 degrees. And what we need to determine here, or what we are asked to determine here, is the velocities of the sliders B and C. That means B with respect to O, C with respect to O, and D with respect to O. The angular velocity of link AC, that means omega AC. So we have to determine here omega AC, and these two are the linear velocities, instantaneous velocities. Then acceleration of the sliders B and C. So that means I have to determine absolute acceleration of B and absolute acceleration of the slider C. These two things I have to determine. And the angular accelerations of the link AB and AC, that means alpha AB and alpha AC. This is what is expected in this problem. So first, until and unless we have all the velocities, we won't be able to get the accelerations of the joints. So first we will go for the velocity polygon. So for velocity polygon, we need to first determine velocity of A with respect to O, then velocity of B with respect to A, and velocity of C with respect to A, then velocity of B with respect to O, and velocity of C with respect to O can be determined. Now here, for this we know, for the crank we know the motion, it is turning clockwise with omega as 60 radians per second. So we can find out this value. So velocity of A with respect to O, this is O is equal to link length OA r omega of OA. So link length is 4 centimeters, omega is 60 radians per second. So velocity of A with respect to O is equal to, coming out 24, so 240 centimeters per second. All these dimensions are given in centimeters. So we get velocity of A with respect to O as 240 centimeters per second. So, and we will interpret the velocities, the direction of the vectors. Now when this is turning in this direction, the velocity vector, velocity of A with respect to O, will be perpendicular to link length, and as it is turning this way, so the vector will be in this direction. And velocity of B with respect to A will be perpendicular to the link AB. Velocity of B with respect to O will be along the line of the stroke. Velocity of C with respect to A will be perpendicular to the link condition CA, and velocity of C with respect to O or the frame will be along the line of action. So first we will draw all these lines so that we are comfortable to get the velocity vectors. So this is how we can show velocity vector of v. A with respect to O will be in this direction, perpendicular. This will be the line of action of velocity of the orientation of vector B with respect to A, and this will be the orientation of velocity of C with respect to A. So these are the velocities which we are supposed to draw. So now we can, as we know, we are comfortable with drawing the velocity vectors, so will directly go for the velocity vector polygon. So first I'll have to decide a scale. So we'll decide a scale. So I take a scale of 1 centimeter as 48 centimeter per second. This as the scale for velocity polygon. Then we locate the pole. So we will locate the pole for the velocity polygon. So somewhere here I locate this pole, and pole is O. So this point is pole. Frame, absolute velocity 0. Then velocity vector of A with respect to O is pointed downwards. So we'll draw the vectors one by one and we'll complete the velocity polygon. So thus we have finished the velocity polygon. So now we can read those values from our velocity polygon and get all the velocity values, so that we are in a position to find out all the magnitudes of the centripetal component of all the joints which are required for the acceleration polygon, right? So we measure velocity of B with respect to A. So B with respect to A, in the velocity polygon it is length AB. It comes out to be 3.5 centimeters. So according to scale, I am getting the actual value of velocity of B with respect to A as 168 centimeters per second. So likewise, now I will find out all the values of the velocity, instantaneous velocities of all the joints. So this is how we get all the velocities of the joints. So thus we have these two answers. Velocity of slider B. Velocity of slider B is B with respect. So this is velocity of the slider B. This is one answer. And velocity of slider C. Velocity of slider C. This is the second answer of the first bit. These two we have determined. So now we'll have to go for the acceleration polygon. So I take a space. So I just, and we'll try to not move away, more away from the configuration diagram, because we'll be requiring the space to draw the vectors. So maybe somewhere here I keep the space for getting the acceleration polygon. So now for acceleration polygon, we need to determine acceleration of the joint A, B, C, right? So first, let us start with the first joint. So the first joint is A. So we'll be talking about acceleration of A with respect to O. Now this will be having two components, as we know. One is the centripetal component of acceleration of A with respect to O, and the other is the tangential component of acceleration of A with respect to O. Now this is equal to velocity of A with respect to A square divided by the link length AO. Right, we know the velocity values here. So this velocity value is A with respect to O is 240, so it is 240 square divided by link length AO is given 4. So this comes out to be somewhere 14,400 centimeter per second square, right? And for tangential acceleration component, this is R alpha. RA is OA, the link length OA, into alpha of OA. Now as in the input condition, the acceleration is not mentioned, so we will consider omega to be constant, right? So this value will, tangential component will become 0. So what is consideration? So considering omega OA constant, therefore alpha A OA is 0. This is what our consideration is. So that means acceleration of A with respect to O will have only one component, which is centripetal component, and the direction of this vector magnitude is for 14,400 centimeter per second square, right? And its direction will be towards the center of rotation. Now for A the rotation is about O, that means the vector will be pointed or directed towards the center of rotation. So that means this will be so from A to O, this is the centripetal component of A with respect to O. So when we are drawing from O point, wherever we will be locating the from pole, this vector will be moving downwards. So similarly, now we go for the second joint, that is B. So we'll talk about second. So acceleration of B with respect to O. Again, it will be having two components. First is the centripetal component of B with respect to A. We will take B with respect to A. So centripetal component of B with respect to A is velocity of B with respect to A square by the link length AB. So it will be so we get the centripetal component as this, and the tangential component of B with respect to A, this will be R alpha. So R is link length AB into alpha of AB. Now again, this magnitude is not known, but this is partially known. At least we know the direction of this vector. Now the direction of the centripetal component of B with respect to A, that means the center of rotation is A, so vector will be pointed towards A and parallel to the link AB, and the tangential component of B with respect to A will be perpendicular to the link condition AB. So this is how the vector will be parallel to AB and towards A. So wherever A, from A this vector will be coming out. So similarly we can find out the B with respect to O. So third will be acceleration of B with respect to O. Now this will be the acceleration will be linear, because slider B with respect to is talking about the sliding motion, so it is just the linear. So this will be the linear acceleration, or simply the tangential component. Now as we know, in this case R will be greater, so if R becomes greater, so the centripetal component is negligible, so it will be having only linear dv by dt, so only having so that we can directly get from the acceleration polygon. So next we will go for acceleration of C with respect to acceleration of C, centripetal acceleration of C with respect to A. Again it will be having two components. So first is centripetal component of C with respect to A, which is equal to velocity of C with respect to A square divided by the link length AC. So C with respect to A. So here we see, so we get the centripetal component magnitude as this value, and again this will be partially known. Now acceleration of C with respect to A, C with respect to A will be directed towards A, and the tangential component will be perpendicular to the link length AC or parallel to the velocity vector. So that we can again get in our configuration diagram so that there is no confusion. So there we have, and finally it will be C with respect to O. So finally we will see acceleration of C with respect to O. Again this is linear acceleration, so it will be having only tangential component, or just the change in the magnitude will give me the acceleration value, so that we can directly get from the acceleration polygon. So now we have to start. Now first before we start, we will have always take a look at the magnitude values, right, so that we are taking a proper scale. So if you see the first vector, it is 14,400, and this is 2,000, somewhere 3,000, somewhere so it's somewhere 3 times or 2.5 times the value. So if I am drawing this as to be the greatest vector, so accordingly we must always decide the scale, so that all the vectors which we are drawing will be proper. So for that, first I'll here decide the scale for this vector. So likewise I decide a scale as 1 centimeter as somewhere 2400 centimeter per second square. See, I have applied the logic like this is somewhere 14,400, this is 3, somewhere 3,000, so 3 5s are 15, so 5 times. So these two vectors will have a, so this vector will be 1/5 of this vector. So we should be comfortable to get the value. So accordingly always decide the scale. So now we'll locate the pole. So somewhere here I locate the pole as O, right? Now the first vector what we are supposed to draw, this is acting towards the center of rotation. So that means from the pole, see this acceleration. So now I am supposed to draw centripetal component of E with respect to O. For that pole I have drawn. So this vector will be in this direction. In this direction it will be drawn. So my direction of my pencil and the vector must be same. So I am not, and it will be parallel to, it is parallel to so I draw the first vector which will be in this direction to according to this scale. but the centripetal component will be of 6 centimeter, the scale which I have decided. So I have taken the first vector as 6 centimeter, so I get this as the point A. So this vector, so I confirm this vector because it is not having any other component, so this vector is absolute acceleration of, so this is, and it is in this direction, so this is absolute acceleration of A with respect to O, right? So now we'll go for B with respect to A. Now B with respect to A, so if we see according to our scale, so centripetal component of B with respect to A is 28, 22. So according to our scale, we will get this value somewhere, so it will be 28, 22.4 divided by 2400. So it is somewhere 1.17 centimeter. So it is, say, it is 11.76 mm. So somewhere 12 mm, right? So anyway, the direction of this vector is in this direction, A, B with respect to A, B with respect to A. So from A this vector will come out. So we have A, so parallel to AB, parallel to AB, we roll it to A, so we roll it to A, and this vector will be coming out in this direction, and length is coming out to be somewhere 12 mm. So I mark 12 mm. So I mark this 12 mm. So now this is not absolute location of B, so we name this as B dash, and this is, so in this direction, so this whatever we have drawn which is in this direction, this is the centripetal component of B with respect to A. Fine. And the tangential component will be perpendicular to this one, so I can match my 90 degree. So the tangential component will be this. So this will be, this line is representing the tangential component of B with respect to A, right? So this is locus of B. Now B with respect to O is along the line of action. So O point we have, so B with respect to O, so again this will be locus of B. So somewhere here, wherever this intersects, that means this point is the absolute location of B. So this velocity, this vector, what we have got, this is absolute acceleration of B with respect to O. This is the tangential component of B with respect to O, and when we join AB, so this vector is the absolute acceleration of B with respect to A. So similarly, now we have to go for acceleration of C. So acceleration of centripetal component will be in this direction, so I can match my roller scale and roll it, so I get the centripetal component, and perpendicular to it I can get the tangential component of it and the line of action of this vector. So I get the, again, as we got the point B, similarly we get the point C here. So thus we have determined all the accelerations of the joint. So what next we have to determine? Acceleration of the sliders B and C. So in the acceleration polygon, I get velocity of B with respect to O. Velocity of B with respect to O as 4.4 centimeters. So this I get as one answer. And C with respect to O, I measure according to scale. If I convert this value, see, logically if you see, this is a single crank moving the same dimensions. Actually this should come out to be same values. So if they are somewhere near values, that means our problem is correct. These are due to from graphical drawing errors involved, but it should come out to be somewhere same values. If you see, the conditions are same for the given. So you forget, if you remove this, you will say this as one slider crank mechanism same as that of this. So these two have same values. So this difference what we are getting, these are due to the drawing errors. So next thing we have to determine the angular velocity of the link. So I'll discuss angular velocity, angular acceleration of link AB. Now the tangential component is related to alpha. So tangential component of B with respect to A will give me alpha of AB. So we get alpha of AB to be as this divided by the link length AB. So from my, so where is this component? So B dash is the tangential component of B with respect to A. So I take this from my acceleration polygon, I convert it to my scale, so I get that value to be as 9600, link length as this. So we get the magnitude as this radians per second square of alpha AB. Now the sense of rotation. So if we see this vector, to reach B from A, I have to move this way and this way. So this is acting in the upward direction. So if I take this vector, it is B with respect to A. So when I place it on B, so vector is pointing outwards with respect to A. So this is turning counterclockwise. So alpha comes out to be counterclockwise. So similarly, then we can find out the angular acceleration of the link ACL as well. So this is how we finish this problem for the acceleration analysis.